So we're continuing our study of the various series convergence tests that we've been looking at. And so far we have considered the general term test, geometric series test, the integral test, and last time we looked at the comparison tests, the standard and limit comparison tests. So I just want to kick off with another example of applying the limit comparison test. We'll have another look at an example of how we use the limit comparison test, and then we'll say something about how it is proved, how the test itself is proved. So for this example, I'm going to take one of the end of chapter exercises. I'm going to consider question 10. Question 10 from page 26. And this question says, consider this series the sum from n equals 1 to infinity, where you've got 2n plus 5 over the square root of n to the power 6 plus n. So considering this series for convergence, we would like to determine whether this converges or it diverges. Okay? And we'll use the limit comparison test. Okay? So to select the comparison series, we look at the dominant behavior of the numerators, and the denominator. Numerator and denominator. Now, what's the dominant behavior here? Well, the numerator is acting like n. Okay, so it's a multiple of n plus a constant. The denominator is really acting like n cubed, okay? Because it's the square root of an expression which is order 6. Okay? When you take the square root of something, you halve the exponents. So the n6, the n to the power 6 becomes an n cubed. So it's kind of looking like an order 1 thing over an order 3 thing. So we will compare with the known convergent series, the sum of 1 over n squared. Now we know this series is convergent because this is a hyperharmonic series, and we've already determined the convergence status of all of these from the integral test. Okay. So we proved it was convergent using the integral test. So we know this is a convergent series. We're going to apply the limit convergence test. So what we do is we investigate the limit as n goes to infinity of our series, the series term 2n plus 5 over the square root of n to the 6 plus n. We divide it by the term from our comparison series. So we're looking at the limit of this quantity here. The term from our series divided by the term from the comparison series. And what we want to do is examine this limit, and when you look at the specifications of the limit comparison test, because we're comparing to a known convergent series, we're going to try and bring this limit out and determine that it's equal to a finite value. calculate the limit and show that it's equal to L, where L is greater than or equal to 0, but strictly less than infinity, so finite quantity. Then dividing by n squared is the same as multiplying the numerator, dividing by 1 over n squared is the same as multiplying the numerator by n squared. So this is the limit of 2n cubed plus 5n squared over the square root of n6 plus n. And now we're into just taking a limit of a sequence. So we can go back and think back and use our techniques for dealing with limits of sequences. We want to use the quotient rule here, because we're taking the limit of a quotient. We want to say it's the quotient of the limits. Of course, yes, question?
If you do that, would you simply 2 over n plus 5 over n squared? Because you'd be counted it by 1 over n squared. Is it 1 over 1 over n squared?
Yeah, so it's 1 over n squared.
Yeah.
So really it's n squared. So this is a fraction, this is the reciprocal of 1 over n squared. So really this whole factor here is equal to n squared, isn't it? Yeah? And then I'm multiplying the other fraction of n squared, so I just multiply the numerator by the n squared. I think we're just getting confused with the 1 over something. So, okay, I want to use the quotient rule for this to say the limit of the quotient is the quotient of the limits. I can't do that at the moment because the numerator is not convergent, nor is the denominator. So I need to divide above and below by the highest power of n that we see. The highest power of n that we see, well, it's not n to the power 6, it's n cubed. Okay? The n to the power 6 is underneath the square root. So we divide above and below by n cubed, so we don't change the fraction, but we do change the way it's represented. And we want to divide this square root by n cubed, so I take the n cubed inside the square root, it becomes an n6. So I'm really dividing by n to the power 6. So this will be 1 over n to the power 5 square root of all that. Okay, now this looks like something that I can apply the algebra of limits theorem for sequences to, because this is a quotient of convergent sequences. So I can say this is the limit as n goes to infinity, 2 plus 5 over n, over the limit as n goes to infinity, the square root of 1 plus 1 over n to the power 5. So that's by the algebra of limits theorem. Sequences. And again, use the algebra of limits for sequences. The limit of 2 plus 5 over n, the 5 over n is convergent to 0, so we have to do 2. And the 1 over n to the power 5 is converging to 0, so the limit of this is going to just be the square root of 1, so it's actually going to be 1. So the whole thing is just going to have the value of 2. Technically, there is an extra property we're using there, which is that the limit as n goes to infinity of the square root of something is equal to the square root of the limit as n goes to infinity of xn. And that is true. The reason we can do it, we'll actually discover it later on in the course, but this is true since the square root is a continuous function. Now we have to discuss in detail continuous functions yet, that we will be when we come on to study it. I mean, it seems intuitive that it will be. Because the thing you're taking the square root of is convergent to 1, the limit of the square root value will also converge to 1. And that's true because the square root is a nice enough, well-behaved function. Central block at the assignment sheet yet? No, that's the Thank you. So, what we found there is we're in the middle of executing the limit comparison test. We wanted to test this series for convergence. We determined its overall behavior was like 1 over n squared. And to confirm that, we took the limit of the ratio of the two series terms, the terms from our sequence, divided by the terms of the comparison series. Evaluate the limit and find that the limit comes out to a fixed finite value. So by the limit comparison test, our series is convergent too. Okay. So that's another example of the application of the limit comparison test. It's kind of equivalent to the standard comparison test, but generally, I don't know, personally I find it easier to kind of construct these limits and evaluate them rather than constructing the inequalities that are called for in the standard comparison test. Generally, I find the limit comparison test an easier one to execute. But we do want to say a little bit of a word about the proof of the limit comparison test. But before we do that, and in order to understand the proof and understand the arguments for some of the tests to come, I want to go back and look at a section which I didn't say anything about yet, and this is section 2.3. And this is a short section on tails. Now, this is not about things attached to the end of your cap or anything. It's about tails of series. So this is a series. It's A1 plus A2 plus etc. 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 AK plus AK plus 1 plus. And there's a bit of terminology that we can use for these series is, if you look at the first part of the series, that's called the partial sum. Not the whole sum, a partial sum. This would be the sum from n equals 1 to k of an. The rest of which there's an infinite number of terms still to come in the infinite series, this we would call the tail of the series, or the infinite tail, starting from k plus 1. Okay, so these are just the terms we can use. The partial sum, which is adding up the series to a certain point, and then the rest of the series then is the tail. The infinite tail. Now, what we just want to emphasize is which bit, when you look at these two bits of the series, which bit is determining the convergence of the series? Well, you see, whether or not this series converges, it's got absolutely nothing to do with any particular partial sum. Right? It's really all about the infinite tail. Whether or not the infinite tail converges. If the infinite tail converges, so if that infinite series has a finite value, infinite tail, then so does the original series. Okay? Because the original series is just equal to the infinite tail plus these numbers at the beginning. And they certainly have a finite value. It's just a load of numbers added together. Finite number of numbers added together. So if the tail converges, then the series converges. On the other hand, if the tail diverges, with that infinite tail that's larger and larger in absolute value, okay, or it just keeps oscillating up and down, it's a mixture of positive and negative terms, and it's just not settling down to a limiting value. So if the infinite tail diverges, then so does the original series. The fact that you add on some particular number, that partial sum, makes no difference to the divergent behavior. Okay? If this thing is growing larger and larger, it's exploding in value, going to infinity, even if you subtracted a huge number from it, it would still be going to infinity. Okay? And the implications go the other way. So that was whatever the status of the infinite tail is, that implies the original series has the same status. And so the implications go the other way as well. If the original series converges, then so does this infinite tail. Because the value the infinite tail has is the original series minus that partial sum. On the other hand, if the original series diverges, so does the infinite tail. The value the infinite tail has is just the same value as the original series, subtracting some fixed number. So basically what we're saying is that the original series converges if and only if the tail converges. Right? And this is true, this statement, this is true for any point k. Okay? Now, why are we going on about this? Well, it's just that in the arguments for the comparison tests, we're going to prove the convergence or divergence of the original series by discovering a particular tail of it. So by homing in on a particular tail, so at the infinite tail of the series from a certain point on, and we're going to be able to say whether that tail converges or diverges. And then the conclusion will be the same for the original series because of this argument. And this is true since the value, whatever value the infinite tail might have, is equal to the value the original series will have, just minus the partial sum. The partial sum is just some fixed number. So if this thing is converging, so will this be, vice versa. If this thing is diverging, so will this. So that's our short remark about tails. And it also means that, like, if you've got a convergent series and you change some finite collection of values, it'll still be a convergent series. Or if you have a divergent series and you go in and you change some finite collection of values in the series, finite number of terms, it'll still be divergent. You can't fix the divergence by changing the series at a finite number of locations, because it'll still have these divergent infinite tails. Okay. So we want to come back then to the proof of the limit comparison test. Or any questions before we use this idea of tails? Queries about it or clarification I could give? Okay, so let's see why the limit comparison test works. Now, the tools that are used here are the definition of convergence for an infinite series and any results we've already proved about any results we've already proved about convergence of series, okay? In particular, the standard comparison test. So we can actually use the standard comparison test, which we proved last time, to prove the limit comparison. Okay? So first we look, now remember, the theorem comes in two flavors. There's a convergent comparison and a divergent comparison. So we'll give the argument for the convergent case. The divergent case is a similar kind of argument. So the divergent, or the convergent case, the first one says, if we take the limit of am divided by cm, where the cm's is a convergent series. If we take this limit, find it to have a value L, which is finite, greater than or equal to 0 and finite, then the conclusion is that our original series is also convergent. Okay. So how is this proved? So we assume that Cm converges and that the limit of am divided by Cm is equal to L, okay, where L is some finite number. Okay, we have to prove now that our series, the sum of am, is also convergent. Well, you can have a little sketch in your number line. Here's 0. L will be some number, well, maybe L is 0 or it's to the right. And we can consider a radius around L like 1. Okay, the lower limit L minus 1 could be negative. It could be to the left of 0. L was close to 0. But I do know that the right edge of that interval, L plus 1, that's definitely a positive number. Okay. So by convergence, there exists a point M such that for all values of the index n greater than or equal to this capital M, we have that the distance of am over cm minus L is strictly less than 1. Now, I'm assuming that these ratios converge to L. So setting epsilon equal to 1 in the definition of convergence for sequences, there must exist some point, capital M, after which the distance between the ratio and L is strictly less than 1. So that means our ratios, am over cm, live inside this interval whenever m is bigger than or equal to capital M. Okay? So we know where they are. We know the ratios are trapped inside that interval for every value of the index little n bigger than or equal to this capital M. Okay? But that implies for all values of m greater than or equal to capital M, am over cm is strictly less than L plus 1. Okay? Because L plus 1 is the biggest number in that interval. So if all our ratios are trapped inside here, they must all be less than L plus 1.
How have you chosen 1 as that?
Yeah, excellent question. Absolutely no reason at all. I could have chosen anything, completely arbitrary. Yeah, that's a good point. We should emphasize when things are just arbitrary choices and when there's some specific reason. You can choose epsilon to be any value whatsoever. All we want to be able to do is to find an upper bound for these ratios at some point. Yeah. So that's an excellent point. choice of epsilon equal to 1 here, where I choose epsilon equal to 1 in the definition of convergence for a sequence, is arbitrary. You got to choose some positive number. It'd be slightly perverse to choose anything apart from 1. If you've got a completely free choice, why not choose the nicest number that there is? Yeah, good point. This argument would work if you chose any positive value for epsilon. Yeah, so then that means that for all m greater than or equal to capital M, AM is strictly less than L plus 1 times CM. So we know all of these numbers are. We also know it's also stated in the statement of the theorem that all the terms of the series we're investigating are non-negative. So we also know that 0 is less than or equal to all the AMs. Okay, that's sort of the statement of the theorem. So what we're looking at here is all of these terms are smaller than some fixed multiple of the terms of a convergent series. So that's exactly the kind of inequality we need to apply the standard comparison test. By the standard comparison test, the tail from the point capital M to infinity of the series AN, this is convergent since the tail of the CN series, and if it just gets multiplied by some fixed number, that doesn't change it, this is convergent also. Okay, we assumed the series CM was convergent. If the series CM is convergent, so is every infinite tail of it. And you multiply it by this number L plus 1, it's still convergent. Okay? And we've shown that the terms of our series from the point capital M are smaller than those terms. So they're even better. Well, remember, series converge because the terms are getting small enough. So the infinite sum is settling down to a limiting value. Well, our terms AM are now behaving even better than those. They're even smaller than those. Okay? And therefore, the whole series, the sum of n equals 1 to infinity of AM, is convergent as it has a convergent tail. So by our remarks about tails before, if the series has a convergent tail, then the series is convergent. Because the bit that's missing, the infinite series, is the value of the tail plus whatever bunch of initial terms lead up to the tail. Just that first part, the partial sum. So that proves the convergent case of the limit comparison test. The divergent case is proved in a similar way. It's described in the notes. So I'll leave you to read through it yourselves. But it's just about choosing. Now the only bit is, note the choice of epsilon is not arbitrary there. When we're arguing for the divergent case, We know L, the L, yeah, if you look at the statement of the divergent case, the limit of AM over DM is equal to L, where L is strictly positive. So we know L is to the right of 0. And there we want to choose our epsilon, we want to choose our radius so that it definitely doesn't become negative. So it definitely stays to the right, to the positive side of 0. And that can be done, we effectively choose epsilon equal to L over 2, I believe. Yeah, choosing epsilon equal to L over 2. So L minus L over 2, and L plus L over 2. L minus L over 2 is, of course, L over 2. So if L is strictly positive, so L over 2, the lower limit of the interval is still strictly positive. You couldn't have used L, you couldn't have used epsilon equals 1, because if you didn't know the precise value of L, the radius 1 could have taken you into the negative side. And you see in the argument for, well, this leads to, in the divergent case, this leads to knowing for every, so I'm going to have to bring it down, but for every little n greater than or equal to capital N, we will know that the ANs are strictly bigger than L over 2 times the DNs, and that these are still strictly positive. So the fact that these terms produce a divergent tail, these terms produce a divergent series, means that these ones will as well, because they're worse behaved than DNs. The series diverge because the terms are too big, or not converging to 0 fast enough. So if those terms DM are too big, well then so must the ANs be. They're even bigger. So that's just a quick sketch of the crucial point in the proof of the divergence. Any other questions about those comparison tests or queries about them that you'd like to ask? Okay, so on the tutorial sheet you'll find lots of questions to practice with on those. Sure. So starting from question 11, there's a bunch of questions on applying the comparison tests. Okay. So either using the standard comparison test, oh sorry, not those questions, sorry. Just these two here. Just those two there, but you'll also find more in the end of chapter exercises. So page 20, it's a big long bunch of test problems, and some of those can be tackled with the comparison tests. You need to get a feeling for which series are susceptible to which tests. Okay? So that can come from experience of trying out the various tests on lots of different series. Okay, so there's a few more tests to get through. One that we'll deal with just a sketch of the argument is the alternating series test. This applies to when the series looks like this. So the presence of this minus 1 to the power n, that's going to produce an alternating plus or minus sign. Okay? So this will be the series minus a1 plus a2 minus a3 plus a4, etc., etc. So the sign in front of the a is alternating. So if the sequence AM, if the AM are all positive, if they're all positive and decreasing, but they're positive decreasing numbers, meaning, yes, so the AM is bigger than AM plus 1, this continues all the while, and they're all bigger than 0, bigger than or equal to 0. Non-negative, perhaps, is a better word for positive. It's okay if they become 0. But if the sequence is decreasing, and the limit of AM is equal to 0, so if the AMs themselves, they're always positive, getting smaller, and they're converging to 0, then the alternating series is also convergent. Again, we don't know what the value of the sum is, just from this information, but we will know that it is convergent. But if the limit as m goes to infinity of the AMs is not 0, then the alternating series will be divergent. So this is the alternating series test. So whenever we see an alternating series, which is one where the terms are alternatively positive and negative, it should be straightforward to determine the convergence of that. It's going to converge if and only if the absolute values of the terms, so that's the AMs, we strip off the -1s, just look at the absolute values of each of the terms. If that is a sequence of terms that is getting smaller and converging to 0, then the original alternating series will converge. Now the sketch of the proof of this is a fairly detailed sketch in the notes of the proof of this, but sketch by picture, we'll just assume. I mean, what does the graph of the partial sums of such a series looks like? Well, in the convergent case, the graph of the plot of all the partial sums will have this kind of feature. So each dot is the next partial sum. The reason they're going up and down, I mean, we might join them by lines just to emphasize the behavior. They're going up and down because the terms of the series are alternating. They're alternatively positive and negative. So the development of the partial sums is you're stepping up and stepping down, stepping up and stepping down, up and down, up and down, up and down. But if the step size, so the step size is this quantity, is the quantity AM. The step size at stage M. If that's convergent to 0, this implies the partial sums are settling down. Settling down or converging to a limit. If the partial sums are changed, the change in the partial sums at each stage is itself convergent to 0, that's going to imply that the partial sums themselves are converging, settling down to some limiting value here. and it indicates it graphically here. So the sum of this series, this would be where the sum of the alternating series kind of equals out. The partial sums are just oscillating ever tightly around the limit up. Whereas if the ANs are not converging to 0, how, what might the plot of the partial sums look like? Well, you're still going to be stepping up and down, but okay, you might start to make smaller steps for a while, but then suddenly you'll be making big steps again. Maybe it settles down, but then there'll be big steps. So if the step size is not converging to 0, we continue to see large steps. So we'll continue to see large changes in the partial sums. And that will prevent the partial sums from settling down to a limiting value. Yes.
More comment than a question.
Okay, go.
Is it kind of reminiscent a little bit of like squeezing lemon? It's so-called the top.
Yeah.
Separate it out into the positives and the negatives, and you get this sort of squeeze.
Yeah. No, it is exactly, because if you look at the more detailed argument, which is in the notes, it actually considers separately, it splits the sequence of partial sums into two subsequences. All the ones that are up here, and separately, a blue pen, all the ones that are down there. So the upper ones and the lower ones. And actually they are squeezed, the infinite sum is always going to be trapped between these two levels. And because those two levels are converging to each other, because the step size is converging to 0, that proves that you're effectively using that squeezing concept.
You just prove that each separate one converges to the limit, and that
Yeah.
an infinite series must.
Yeah. And each separate one does converge because each of the blue ones is always going to be less than the red one. So the blue ones consist of an increasing sequence which is bounded above. And an increasing sequence bounded above will always be convergent by the monotone convergence theorem. And equally, the red sequence, the sequence of top ones, they're decreasing, but they're always bounded below by any of the blue ones. So therefore, that's a decreasing sequence which is bounded below, so that will be convergent by the monotone convergence theorem as well. So yeah, the more detailed argument, so the monotone convergence theorem is quoted in the more detailed argument. But it's a kind of the pictures are fairly suggestive of the reasoning, of the ideas and the concepts. Okay? So this is not convergent behavior here, certainly. All right, not convergent behavior. I mean, you can never tell because you're only seeing a finite part of it there, but if this pattern continues, the step size is not settling down to 0. We continue to observe sporadic large steps. That means the partial sums are not settling down, not converging to it. Okay. So tomorrow, kind of save the best for last, which I think is one of the nicer ones. We'll look at the ratio test. And this is a night where we'll discuss the proof of that in full detail. The proof of it is a nice combination of lots of previous ideas, of the comparison test and the geometric series test. Okay. So we'll look at the ratio test tomorrow, and then that will be, there's one small one then at the end called the root test, but that will kind of complete our family of convergence tests and nearly bring us to the end of the chapter as well. Okay? So I'll see you again at this time tomorrow.